All right. The last speaker of this session is Andy ZHOU from the University of California at Berkeley, presenting memory efficient, limb position aware hand gesture recognition using hyperdimensional computing. Take it away, Andy.
All right. Thanks for the introduction. And thanks everyone for coming to my talk and for your interest in my research. I'll be presenting on a hand gesture recognition algorithm using hyperdimensional computing with some considerations for edge implementation. So hand gesture recognition has many potential applications in human-computer interaction as well as rehabilitation, and it's often performed using electromyography or EMG. Using a wearable device such as this one I've shown, we can record EMG signals from the forearm that represent the neural and muscular activity corresponding to a user performing some sort of movement of their hand or fingers. The goal of gesture recognition is to take a segment of this data, process it, and then infer the gesture that the user is performing. In this case, it could be the individual flexion of the middle finger. And ideally, we want to do all of this within the device itself, precluding the need to wirelessly stream all the raw data to a companion device and reducing the overall latency of the system. So the classification algorithm that we chose to implement for this is hyperdimensional computing, or HD computing, where we represent our data, in this case, segments of EMG signals, as very high dimensional vectors or hypervectors. I'm not going to go through the details of this transformation, but I do want to point out that it involves only simple element-wise operations performed on randomly generated 10,000-bit bipolar hypervectors consisting of plus and minus ones. Once we've projected our EMG signals into their hypervector representation, classification can be performed as follows. Training is done through superposition of all of the training examples corresponding to a single gesture class, which forms a prototype hypervector for that class. And prototypes for each of the classes are then stored in an associative memory, which constitutes the model parameters. Finally, for inference, a new query hypervector is compared to each prototype in a nearest neighbor search using cosine or Hamming similarity as a metric. And the fact that training is performed through a single pass accumulation of training examples is what makes HD computing attractive for tasks where we might encounter new situational contexts after our model has been deployed. So for gesture recognition, one such change in context could be movement to different limb positions. Limb position change can affect the EMG signal through addition of background activity from other muscles, movements of the electrodes on the skin and change in the skin electrode interface, as well as changes in the shape and the activity of the target muscles themselves. And often an initially trained model isn't generalizable to all of these confounding factors, which results in degradation of the classification accuracy. So to fix this, we can either greatly expand the initial model training effort, or we can implement on-the-fly model updates, which in the case of HD computing is again just continuous accumulation of new training examples. We've actually demonstrated this before in previous work, where we've taken the entire HD classification flow and implemented it in the FPGA onboard our wearable EMG sensor. And we were able to achieve about 125 microjoules per example when training, performing inference, or updating the model. And we demonstrated that with an experiment in 2 different limb positions. We first trained an initial model using the device in the baseline limb position, and we tested it in both the same position where it performed very well, as well as in the new position where it performed much more poorly. Next, we updated the model in this new position by superimposing new training examples onto the existing prototypes, and we again tested it in both limb positions, this time achieving better accuracy in the new limb position while still maintaining good performance in the initial one. And to reiterate, this entire process was performed in one sitting with all the computations done on board the wearable device. So the big question that we're trying to address in the work I'm presenting today is, how does all of this scale to a larger number of contexts? To answer that, we collected a larger data set consisting of the same 13 gesture classes as in the previous experiment, but performed in the 8 different limb position contexts that I've shown here. And I'll give you a preview of what we found. First, direct superposition of examples from all the contexts enables some generalization, but that performance degrades with an increasing number of contexts. Second, if we know which context we're in, and if we can store context-specific parameters separately, then we can perform dual-stage classification with a high degree of accuracy, but at the cost of maintaining a much larger memory for parameter storage. And finally, the main innovation that I'm presenting today is sort of a best of both worlds approach, where by encoding context information using sensor fusion with accelerometer signals, we can achieve high classification accuracy while still supporting superposition of model parameters for efficient use of memory. So first, a demonstration of what happens with normal superposition. We can break the training process down into two steps. The first step is accumulating all of the training examples from each context and each class into context-specific class prototypes, which can be gathered into context-specific associative memories, which I've denoted here as AM0 through AM7. For the baseline generalized classifier, these separate associative memories are just again superimposed with each other, forming an overall associative memory that covers all of our different limb positions and that we can use to then classify a new query hypervector. If we plot the classification accuracy versus the number of contexts being included in the classification task, we see more error for a larger number of contexts. We clearly do the best when we only train and test within a single context, and that's what we'll call our within context accuracy, or our best case scenario. Compared to this, if we try to encompass all 8 limb position contexts, we experience 23% more error compared to that within context case. So to get an idea of where this degradation is coming from, we can inspect the similarity calculations that are used during inference. These similarities are found using dot products between a query hypervector X from some context C and the trained superimposed prototypes for each gesture. We can decompose this dot product into similarity with prototypes from the same context as our query, some with the remaining similarities from other context prototypes. And we identify this first term as the within context classification, which we know is very accurate. And we can identify the second term as interference from other contexts. Now, this interference term is typically not very small, since it's still expected that there's some degree of similarity between prototypes of the same gesture, even from different contexts. So the goal then is to try to isolate that first term or to nullify the second interference term. In the simplest method, isolation can be achieved by getting rid of the superposition step altogether. And this is what we describe as a dual stage architecture. So here we show our separately trained associative memories that are specific to each context. And instead of superimposing them, we're going to keep them separate. During deployment, we select which associative memory we want to use with a context classifier. So for our experiments, we captured both the EMG signals as well as signals from a 3-axis accelerometer on board the device. And we can run the accelerometer signals through a simple linear classifier to determine the limb position context and select the appropriate set of parameters to then use for inference of a new query. This is a very common approach, and it's often used in the literature for gesture recognition in different limb positions. And as we expect, we perform very well with the best case accuracy maintained for an increasing number of contexts, as shown in the orange data here. However, the main challenge with this approach is memory efficiency. Since we're no longer superimposing our different contexts, the number of parameters that we must store increases with the number of contexts that we learn. And this is not ideal for any edge implementations of this algorithm. So the question is, how can we get the model compression benefits of superimposing the different contexts together without the interference that produces misclassifications? For this, we turn to our method that we're going to call context-based orthogonalization. So we first return to that similarity calculation, and once again, we're trying to nullify the interference term shown here in red. To do this, we're going to depend on two nice properties of computing using bipolar HD vectors. The first is that binding a vector with some different dense hypervector through multiplication rotates it to an orthogonal region in the space. So in this example, binding the vector B to some vector A results in a new vector that's orthogonal to the original vector A and is also likely to be orthogonal to any other vector that we may encounter in our process. The second nice property is that a bipolar vector is its own inverse, meaning that binding a vector with some other vector twice just returns the original vector. So armed with these two tools, we now have a way to approximately remove that interference term. Again, we're going to start with our context-specific associative memories. Now, before we superimpose them, we first bind them with the context hypervectors representing the different limb positions. And we require that hypervectors representing different contexts be orthogonal, which we achieve by generating them randomly. During the inference step, we also bind the query hypervector with its associated context hypervector, which can be determined through classification of the accelerometer signals. If we now again expand our dot product into within context and interference terms, we can see where our two properties of HD vectors can be put to use. In the upper within context term, we get two of the same context hypervectors canceling each other out. And in the lower interference term, we get two orthogonal context vectors that drive the term to zero. Ultimately, our similarity calculation looks almost identical to within context classification, now with the addition of a much smaller interference term than when we were using direct superposition. So here are the results for when we apply this to our gesture recognition task with the new accuracies shown in green. For more than two contexts, we see a clear improvement in using context-based orthogonalization compared to the baseline model with direct superposition, despite the fact that both models utilize superposition of model parameters and have the same parameter memory footprint. The efficacy of this method still varies with the number of superimposed contexts, and we explore this through simulations covered in more detail in our paper. But for 3 or fewer contexts, we actually don't expect any improvement in classification margin at all. Additionally, superposition of an even number of contexts can potentially cause slight degradations in accuracy because in keeping bipolar vectors instead of integer vectors, we use an element-wise majority vote rather than integer addition to perform the superposition. And this may explain the poor performance for 2 contexts. However, for our task with 8 different limb position contexts, there's only about a 5% drop in accuracy compared to the context-specific or the dual stage classifier, despite requiring only 1/8 memory allocation. And this is the best of both worlds behavior that I alluded to earlier. We get to take advantage of model compression through parameter superposition, while we also get the accuracy boost from context-specific classification. So lastly, we wanted to try and remove that requirement of limb position context classification for situations where predetermined or well-defined limb position contexts may be unknown or undesirable. So in these cases, we can directly encode accelerometer signals into context vectors on an example-by-example basis. And we perform this using what's called a continuous item memory, where we use hypervectors to represent quantized levels of some continuous value, which in this case is the acceleration. Relationships between the different values are preserved, with extreme values being represented by distant hypervectors and neighboring values represented by similar hypervectors. And we allow a separate encoding for each axis of the accelerometer, where we can optimize both the number of quantization levels as well as the distance between vectors representing extreme values. Again, in this architecture, accelerometer context hypervectors are encoded on an example-by-example basis, and so they're bound to the EMG vectors during the initial accumulation process. The rest of this architecture looks exactly like the baseline direct superposition case, except that query vectors are also bound to their associated accelerometer context vector. The performance of accelerometer context encoding is shown here in the red points, and it's still a drastic improvement over direct superposition without encoding, but it's slightly worse than orthogonalized context encoding, which was shown in green. Now, this is expected since it's no longer guaranteed that context vectors representing 2 different limb positions are exactly orthogonal. Still, the benefit of this encoding method is to not have to define actual discrete limb positions and not having to implement a separate limb position classifier. So, to summarize what I've presented in this talk, when analyzing the trade-off of classification error versus parameter memory footprint for HD classifiers, we first identified 2 baseline cases. Dual stage classification gave us the best accuracy, but cost the most in terms of memory, since we had to store all of the context-specific parameters separately. On the other hand, direct superposition enabled us to compress our model size by superimposing parameters, but the interference that resulted drastically increased classification error. We introduced a method of context-based orthogonalization where, using classified contexts, we bound context information to our hypervectors and enabled superposition with less interference. And this gave us almost 18% less classification error compared to direct superposition with the same memory footprint. Or looked at another way, we achieved an 8x memory reduction compared to dual stage classification with only a slight increase in error. Within this new space, we also identified ways in which we could trade off the complexity of defining and classifying discrete limb position contexts with a little bit more error using direct accelerometer encoding. At the end of the day, what we're really trying to achieve is continuous model updates on edge devices, and these two methods extend the ability to do so through continuous superposition of new training examples with context encoding. And so this concludes my talk, and I'd like to thank my advisors, Professors Jan Rabai and Ricky Moeller, as well as all of my collaborators in these research groups. And I'd like to mention the various funding sources for this research. And thanks again for listening. So I'm happy to take some questions.
Okay, nice talk, Andy. I don't see any questions coming in on the feed, but I wanted to ask you a question about the sort of the hardware angle here. So, you know, you just showed like the relative reduction in the required parameter memory. In terms of absolute requirements, like how much memory are we talking about here? And do you have some insight into, you know, what you think are appropriate hardware devices for this type of wearable?
Yeah, so for this specific implementation, since we're dealing with 13 gestures and we're using 10,000-bit class prototype vectors, this ends up for just the parameters, it'll be a 130 kilobit memory required for that. And so this isn't with any optimization for, you know, necessarily implementing this in hardware, but we could potentially scale that dimensionality for the vectors down a bit. In terms of what type of hardware this would likely go on, in the past we've implemented, you know, custom RTL for running this in an FPGA, mainly because all of the operations that we perform in the projection and in the classification are all element-wise and should be massively parallel across the 10,000 bits or the, you know, few thousand bits that we want. And so yeah, so custom hardware is definitely the way to go for that. Or I know some people in my group are developing custom HD specific processing units as well. So it would require that sort of device. Yeah.
Yeah, and I assume there's fairly tight power and heat requirements around this type of device as well.
Definitely for a wearable, yeah, you want it to last a long time and not really affect the user at all in terms of the amount of processing, yeah.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, EdgeCortex, Hotchi, and Synsets.